In this chapter, we shift from making models more accurate to making them practical to deploy. The focus is on how to reduce latency and cost without losing the value of the model. New models will keep changing, but the need to run them efficiently does not. Here, we move from model quality to the equally important question of how to make inference faster and cheaper. A model can be technically good and still be unusable if it's too slow or too costly. In real systems, delay and expense directly affect user experience and whether the model is worth deploying at all. Inference optimization can happen at multiple layers. You can improve the model itself, choose better hardware, or tune the service that runs the model so the whole system works more efficiently. The service layer is where the model meets real traffic. It has to schedule requests, use the hardware well, and adapt to usage patterns so latency stays low and resources are not wasted. That is why this field brings together many roles. Improving inference often requires coordination across modeling, systems, compilers, hardware, and data center operations. This chapter will look at the main bottlenecks in AI inference and the techniques used to remove them. Most of the discussion will center on model and service optimization, with a brief look at AI accelerators. Performance gains often come with trade-offs. Lower precision can make a model smaller and faster, but the best hardware may increase performance at a higher price. So optimization always means balancing competing goals. More teams are now building their own inference services, but even if you do not, these ideas help you evaluate tools and diagnose problems. If latency or cost is hurting your application, this chapter gives you a way to think about why. In this section, we're building the vocabulary for inference optimization. First, we'll separate training from inference, because most performance work happens when a model is being used, not built. An AI model has two phases: training, where the model is created or adjusted, and inference, where it is used to produce outputs from inputs. If you're not training or fine-tuning the model yourself, inference is the phase you will usually care about most. This section gives us the common terms we'll use throughout the rest of the chapter. If these ideas already feel familiar, you can move quickly to the part you need. In this section, we'll define what an inference server does and why it matters in production. Then we'll look at the main bottlenecks that shape how you design and optimize it. An inference server is the part of a production system that actually runs the model. It receives requests, uses the available hardware to execute the right model, and sends the result back. In a broader inference service, it sits alongside routing and pre-processing logic. That gives us the basic flow: request in, model execution in the middle, response out. Keep that picture in mind because the rest of the chapter is about making this path faster and more efficient. Notice the separation of roles here. One layer handles incoming traffic, and another layer performs the model inference. That split is important because it lets you scale, route, and optimize the service independently of the model itself. This figure shows the overall service layout in a compact form. The key idea is that inference is not just model execution. It is part of a full service pipeline. If you use a hosted API from a provider, many of these engineering details are handled for you. But if you run the model yourself, you own the entire inference service, building it, tuning it, and keeping it reliable. Now, we shift from architecture to performance. The central question is, what limits the speed of inference in practice? Optimization starts by identifying the bottleneck, not by guessing. In inference, the main limits are usually either the amount of computation required or the rate at which data can move through memory and hardware. A compute-bound task is limited by processing work. If the math takes most of the time, then making the processors or the computation itself more efficient is what improves performance. Password decryption is a good example because the runtime is dominated by heavy calculations. The important point is that the machine is busy doing math, so the bottleneck is compute. A memory bandwidth-bound task is limited by how fast data can move. Even if the processor is fast, performance stalls when the system cannot feed it data quickly enough. This often shows up when data has to move between CPU memory and GPU memory. In practice, that transfer can become the slow step, so the literature often shortens this to memory bound. In this section, we need to be careful with terminology. Memory-bound is sometimes used in two different ways, and the distinction matters for performance analysis. Some people use memory-bound to mean the task simply does not fit in memory. In that case, the problem is capacity, and the practical symptom is often an out-of-memory, or OM, error. That sounds like a capacity problem, but in practice you can often split the workload across devices or across CPU and GPU memory. Once you do that, the real cost becomes data movement, so the bottleneck is usually better described as memory bandwidth. A standard way to classify a workload is with a roofline chart. The key quantity is arithmetic intensity, how many operations you do for each byte you move from memory. Once you know the bottleneck, the fix changes. Compute-bound workloads benefit from more compute, while memory bandwidth-bound workloads benefit from faster memory or higher bandwidth hardware. This chart shows the basic roofline idea. The shape tells you whether performance is being limited by compute or by memory movement. Notice that the axes are on a log scale, which helps compare workloads across a wide range. This figure is the visual reference for roofline analysis. Keep it in mind as we map real workloads to either the compute roof or the memory bandwidth roof. Not every AI workload behaves the same way. Image generation often pushes compute harder, while autoregressive language models often spend more time waiting on memory access. To make this concrete, let's look at transformer inference. It has two distinct phases, and each phase stresses the hardware in a different way. First is prefill. This is the stage where the model reads the prompt and processes those input tokens together. Because those input tokens are handled in parallel, the limit is how many operations the hardware can execute per second. That makes prefill compute-bound. Next comes decode, where the model generates the answer token by token. This phase behaves very differently from prefill. During decoding, the system keeps loading large model weights and other data into the GPU. The pace is then limited by how quickly memory can feed the chip, so decode is memory bandwidth bound. This next figure ties the two phases together. The important thing to notice is that one phase is about parallel processing, while the other is about repeated token generation. The diagram makes the inference pipeline easier to visualize. Watch for the transition from processing the input sequence to producing one output token at a time. This figure labels the two inference steps clearly, and the end-of-sequence token marks when generation stops. It is a simple diagram, but it explains a lot about why language models have different bottlenecks in different phases. Because the two phases stress hardware differently, production systems often run them on different machines. That lets each stage be optimized for its own job. The bottleneck also changes with request shape. Long contexts, long outputs, and batching strategies all affect whether the server is mostly waiting on compute or on memory bandwidth. Today, many AI workloads end up limited by memory bandwidth because transformers are so dominant and accelerator memory systems still have limits. Over time, better hardware and software should shift more of these workloads toward compute-bound behavior. Now, though we understand bottlenecks, we can talk about how services are exposed to users. The next distinction is between online APIs and batch APIs. Providers usually offer two modes for inference. One is optimized for immediate responses, and the other is optimized for efficient large-scale processing. We can think of the two modes as a trade-off between responsiveness and efficiency. Online APIs start work as soon as the request arrives. The goal is to give the user a response with the smallest possible delay. The batch side of the trade-off looks very different. Batch APIs can wait, group requests, and use cheaper hardware more effectively. If latency is not strict, that flexibility can cut costs significantly, even if the response takes hours instead of seconds. The boundary is not absolute. Online systems may still do small amounts of batching as long as users do not feel the delay, but the main goal remains low latency rather than maximum throughput. This is where application requirements matter. Chatbots and code generation usually need fast interaction, while background jobs can tolerate delay and use batch processing instead. Here are some examples of workloads that fit batch processing well. Generating synthetic data is a classic batch workload. You usually care more about total cost and throughput than about immediate turnaround. Another category is periodic analysis and reporting. Tasks like summarizing messages, checking brand sentiment, or reviewing support tickets are often scheduled jobs. They do useful work in the background without requiring an instant answer. Some batch jobs are also part of onboarding and migration workflows. If you need to process many uploaded documents during onboarding, batch processing can make that workload far more economical. Model migrations also fit this pattern. When you switch to a new model, you may need to reprocess large datasets. That is a large, finite job, so batch APIs are a natural fit. Large-scale personalized content is another good example. If you're generating recommendations or newsletters for many users, you can process them in bulk instead of serving each one interactively. Knowledge-based refreshes also work well as batch jobs. Reindexing an organization's data is another example where delay is acceptable. Since the work is planned ahead of time, batch execution improves efficiency. Online APIs often return tokens one by one in streaming mode. That helps users see progress sooner, but it also means the system cannot fully evaluate the response before showing it. There is an important warning here. Batch APIs for foundation models are not the same thing as batch inference in traditional machine learning. In traditional ML, batch inference and online inference are defined by when predictions are computed. Foundation model APIs use those words a little differently, so we need to separate the two meanings. The traditional definition is straightforward. In online inference, the model waits for a request and then computes the prediction in response to it. The prediction is created on demand. Batch inference is the opposite timing model. In batch inference, predictions are generated before users ask for them. The system does the work ahead of time and simply looks up the result later. That works well when the input space is finite and predictable, like recommendations for known users. With foundation models, prompts are open-ended, so it is much harder to pre-compute everything in advance. In this section, we'll define the metrics that matter for serving language models. The key idea is that user experience, service efficiency, and cost are related, but not the same thing. From a user's point of view, latency is usually the main concern. But if you're building the service, throughput and utilization also matter because they directly affect how much the system costs to run. Let's break latency into smaller pieces. For generated text, the first token and the later tokens behave differently, so we measure them separately. Latency is the total time from when a user sends a prompt until the full answer is ready. In streaming systems, that total time is often best understood as a combination of startup time and per token generation time. The first important metric is the time until the model starts responding. This is the part users notice most when they're waiting for the conversation to begin. TTFT measures how long the pre-fill step takes before the first visible token appears. Long prompts usually increase it, and different applications tolerate different values. A chatbot needs a quick start, while document summarization can afford more delay. After the first token, the model has to keep generating the rest of the answer. That ongoing generation speed is the next metric to watch. TPOT measures how quickly each token is produced after generation has started. If that number is high, long responses become painfully slow even if the first token arrived quickly. In streaming mode, the goal is not extreme speed, it's to stay ahead of the reader. For most applications, something around human reading speed is already good enough. You'll also see two closely related terms: time between tokens and inter-token latency. They describe the same general idea: the delay between consecutive output tokens. Both of these metrics focus on the gap from one output token to the next. They're just alternate names for the same timing pattern in generation. This simple equation shows how the pieces fit together. A fast first token helps, but the total time still grows with the number of tokens and the per token speed. Two systems can have the same total latency and still feel very different. That's why you sometimes trade a faster start for slower token generation, or the reverse, depending on what your users value most. Be careful about what you measure. In chain of thought or agent workflows, the model may spend time on hidden internal steps before the user sees anything. So user visible latency can be much longer than model internal timing. Now let's look at why those measurements can diverge. The model may do several internal actions before it ever shows a final response to the user. First, the model forms a plan internally. That work happens before the user sees any answer. This step is part of the model's hidden reasoning process. It may be necessary for good results, but it does not count as visible output. Next, it may take actions and inspect the results. Again, that work is internal and not yet part of the response the user receives. These intermediate results can improve the final answer, but they still aren't displayed. From a user's perspective, the wait is still happening. Finally, the model writes the answer that will actually be shown. That is the point where user visible latency really starts to matter. This is the first output the user can see. So when you measure TTFT for an agent, you usually want the first visible token, not the first internal token. That difference is the key point. The model may start generating early, but the user only experiences latency when the final answer begins to appear. Averages can be misleading because one slow request can distort the whole picture. If a single request takes a second while the rest are fast, you need to investigate the cause instead of trusting the mean. Percentiles are much more useful for latency analysis. P50 tells you the median experience, while P90, P95, and P99 reveal whether a small fraction of requests is getting much slower. Next, we move from waiting time to capacity. Throughput tells you how much work the service can do, and Goodput tells you how much of that work actually meets your service goals. Throughput measures how many output tokens the system can produce across all users. It is a system-level capacity metric, not a per-request metric. Input processing and output generation stress the hardware differently, so it's better to track them separately. If someone says throughput without a qualifier, they usually mean output tokens. Tokens per second is the common unit, and tokens per second per user helps you see how performance changes as load increases. That makes it easier to understand scaling behavior. You can also measure how many requests finish in a time window. For long-running model calls, requests per minute is often more practical than requests per second, especially when concurrency and throttling matter. Higher throughput usually means lower cost per token, because the fixed hardware bill is spread over more generated output. That makes throughput a direct part of the economics of serving models. Pre-filling has its own cost, and you should account for it separately from decoding. Long prompts can make this part significant. The total request cost is just the sum of those two pieces. Once you separate them, you can see where the real spending is coming from. There's no single good throughput number. It depends on the model, the hardware, and whether your prompts and outputs are stable or highly variable. Raw throughput comparisons can be fuzzy because tokenization differs across models. For that reason, cost per request is often a more honest way to compare serving systems. This is the classic systems trade-off. Batching can raise throughput, but it usually hurts latency. In practice, teams often accept higher throughput only when they can live with slower TTFT or TPOT. That trade-off is why throughput alone is not enough. Goodput measures only the requests that actually satisfy your latency and quality targets, so it reflects the user experience more honestly. In this example, the service completes 100 requests per minute, but only 30 meet the target latency limits. So the real useful capacity is 30 good requests per minute, not 100. The figure visualizes the idea that not every completed request counts equally. The useful portion is the part that meets the service objective. Notice how the chart separates total completions from the subset that satisfies the target. That gap is exactly what Goodput is meant to expose. Now, let's look at efficiency of the hardware itself. Utilization metrics tell you how fully you are using compute and memory, not just how many requests you are finishing. Utilization is a simple idea. How much of a resource is actively being used compared with how much is available? But the exact definition matters a lot in practice. The common NVIDIA GPU utilization number only tells you whether the GPU was busy, not whether it was busy efficiently. A device can look fully utilized and still waste most of its potential. That example shows the problem clearly. A GPU can report 100% busy even while doing very little useful work. So we need a metric that measures actual compute delivered. That more meaningful metric is MFU, or model flop/S utilization. It compares the throughput you actually get against the theoretical maximum your hardware could deliver. If a chip could theoretically produce 100 tokens per second, but your service only achieves 20, then your MFU is 20%. The ratio tells you how far you are from the hardware limit. Memory bandwidth matters too. So MBU measures how much of the available bandwidth your inference job is consuming. This is especially important for large models, where memory traffic can become the bottleneck. For LLM inference, bandwidth usage can be estimated with a simple formula. It combines model size, bytes per parameter, and token rate. This expression estimates how much memory traffic the model creates per second. The bigger the model or the faster it generates tokens, the more bandwidth it consumes. Once you know the used bandwidth, you can compare it with the hardware's theoretical limit. That gives you a normalized utilization number. This formula turns bandwidth usage into a percentage of peak capability. It's the same idea as MFU, but for memory instead of compute. Let's plug in concrete numbers so the formula is less abstract. A 7B model in FP16 already moves a lot of data every second. This is the estimated bandwidth demand. It shows why large models can quickly become memory bandwidth bound, even when the compute is not fully saturated. That is one reason quantization matters. Fewer bytes per parameter means less bandwidth pressure, which can improve serving efficiency. Now compare the workload demand with the GPU's maximum memory bandwidth. The ratio tells you how much of the hardware's memory capability you are using. So in this example, the service is using about 70% of peak bandwidth. That means memory access is already a major part of the workload. Because throughput is linearly related to both MFU and MBU. People sometimes use throughput as a rough proxy for utilization, but the underlying bottleneck still matters. Compute-bound workloads tend to show high MFU, while bandwidth-bound workloads tend to show high MBU. The right target depends on which resource is limiting performance. Training often gets better MFU than inference because the workload is more predictable. Within inference, prefill is usually more compute-heavy, while decoding is often more bandwidth-heavy. This table gives real-world MFU examples from large-scale training runs. The numbers show that even very large systems do not always get close to peak hardware efficiency. This example shows how bandwidth utilization can change as concurrency grows. More users can shift the system from being bandwidth-bound toward being limited by compute. Notice the downward trend across the hardware options as concurrency changes. The point is not just the absolute value, but how the bottleneck shifts with load. This figure reinforces that utilization is workload dependent. Different chips can behave differently as user count rises, so you should always read utilization in context. The final takeaway is simple. Higher utilization is useful only if it improves speed or cost. A chip that looks busy but is slow and expensive is not a win. In this section, we'll look at the hardware behind modern AI systems. The main idea is that hardware choices shape both speed and cost, especially when we care about inference. Software optimizations matter, but the underlying chip still sets the ceiling. Here we focus on inference hardware, and the same ideas also help you think about training. AI progress has always depended on available compute. In the 1970s, limited hardware contributed to the first AI winter, showing that ideas alone are not enough. Deep learning took off when GPUs made large-scale training practical. AlexNet is famous partly because it showed researchers could train big models without needing thousands of CPUs. Now, let's define the term. An accelerator is simply a chip built to speed up a particular workload, and in AI, that usually means work on neural networks. AI accelerators are specialized for AI tasks. And today, the dominant example is the GPU. NVIDIA has been the biggest commercial winner in that market. The key contrast is purpose. CPUs are built for general computing, while GPUs are built to run many operations in parallel. This is the first side of the comparison. CPUs handle a wide range of jobs well, especially ones that need strong single-thread performance. A CPU usually has a relatively small number of strong cores. That makes it ideal for the operating system, I/O, and other sequential control tasks. Now compare that with the GPU side, where the design goal is not one fast core, but many cores working together. GPUs trade a few powerful cores for thousands of smaller ones. That structure fits matrix multiplication especially well, which is why it matches machine learning so closely. The more you optimize for parallel work, the harder memory design and power delivery become. So accelerator performance is always a balance, not just a speed race. NVIDIA GPUs inspired a whole ecosystem of AI chips. Some are general-purpose GPUs, while others are more specialized, like TPUs, Gaudi, IPUs, LPUs, and Cerberus systems. A major trend is that inference can cost more than training once systems are deployed. That's why chips optimized for serving models are getting so much attention. Training needs more memory because of backpropagation, and it usually cares about throughput. Inference is different. The goal is low latency and efficient response time. That is why inference accelerators often emphasize fast memory access and lower precision. Examples include Apple Neural Engine, AWS Inferentia, MTIA, and edge chips like Edge TPU and Jetson. Specialization could go even further, down to a model family like transformers. Many accelerators are built for data centers, while others are designed for phones and laptops. Different chips support different memory layouts and compute primitives. To use them well, you need to match the model's data structure to the hardware strengths. This diagram is here to remind you that hardware is layered. The important thing is to notice that different parts of the system are built for different kinds of computation and storage. This figure shows the basic building blocks of computation. As hardware evolves, chips move from scalar operations to vector and tensor operations to better fit AI workloads. Modern GPUs now include tensor cores, and TPUs are built around tensor operations from start. The lesson is simple. Performance improves when the model's layout matches the chip's native primitives. Chip datasheets can be full of details, but three numbers usually matter most: compute, memory, and power. We'll use GPUs to make those ideas concrete. First, let's talk about raw compute. This is the chip's ability to perform operations per second, and it is usually the headline number in a spec sheet. Compute is often measured in flops/s, meaning floating point operations per second. The peak number is theoretical, so in practice you also care about utilization, how much of that peak you actually reach. Higher precision usually means fewer operations per second, because each number costs more to process. So the same chip can look very different depending on whether you run FP32, FP16, or FP8. This table points out that flops/s depends on numeric format. On a modern GPU, lower precision can dramatically increase the advertised compute rate. These numbers show the effect clearly. As precision gets lower, peak throughput rises. The note about TF32 is important too, because the label does not always match the effective bit width exactly. Next comes memory. For AI workloads, memory is not just about how much you have, but also how fast the data can move to the compute cores. A GPU can only stay busy if data arrives quickly enough. Large models and training batches make bandwidth critical, which is why GPU memory is faster and more expensive than CPU memory. CPUs usually rely on DDR/SDRAM, while high-end GPUs often use HBM. The important difference is architectural. GPU memory is built for much higher bandwidth. An accelerator does not have just one pool of memory. It interacts with system memory, dedicated device memory, and very fast on-chip memory, and each layer has a different trade-off. At the top of the hierarchy is CPU memory, which the accelerator can access through the host system. It is large and convenient. but it is usually the slowest of the three levels. This is the memory shared with the CPU, so is the easiest place to start. But because it sits farther from the accelerator cores, it is not the best place for high-speed AI traffic. System memory is relatively slow compared with accelerator memory, but can be quite large. That makes it useful as general-purpose workspace, not as the fastest path for computation. Now move one level closer to the chip. HBM is dedicated GPU memory, placed near the accelerator so data can move much faster. Because this memory belongs to the GPU, it is designed for fast access by the accelerator itself. That makes it the main working memory for large models. HBM offers far higher bandwidth than system memory, which is exactly what high-throughput AI workloads need. The trade-off is that capacity is still limited compared with host memory. The fastest memory is on the chip itself. This tiny memory is used for data and instructions that the cores need almost immediately. Caches, register files, and shared memory all live very close to the compute units. They are small, but they are essential for keeping the GPU fed with data. On-chip memory is incredibly fast, but there is very little of it. That is why GPU programming is often about careful reuse and data movement. This pyramid visualizes the memory hierarchy nicely. As you move downward, memory gets larger but slower. As you move upward, it gets faster but much smaller. Keep this hierarchy in mind. The exact numbers vary by chip, but the trade-off always looks the same. Fast memory is scarce, and large memory is slower. A lot of GPU optimization is really about using the memory hierarchy well. That is why tools like CUDA, Triton, and ROCm matter. They give developers more control over memory access patterns. The last major factor is power. Once chips get fast enough to run billions of transistors at once, energy and cooling become major engineering constraints. Every operation depends on transistors' switching states, and that costs energy. At scale, the result is serious heat, which data centers must remove continuously. The energy cost of accelerators is large enough to matter for both budgets and the environment. That is why compute scaling is now limited not only by chips, but also by power infrastructure. Power is usually reported in two ways: maximum power draw and TDP. They are related, but they do not mean exactly the same thing. This is the first definition, which tells you the absolute upper limit under load. Maximum power draw is the peak the chip could reach when pushed hard. It is the most direct way to think about worst-case electrical demand. Now, the second definition gives a practical cooling target for the system. TDP is the heat the cooling system must handle under typical workloads. In practice, peak power can run somewhat above TDP, so it is a useful guide, but not an exact measurement. If you use cloud providers, you may not manage the cooling yourself, but the electricity still matters. It affects cost, capacity, and the environmental footprint of AI systems. In this section, we will look at how to choose the right accelerator for a workload. The key is to match the hardware to the bottleneck, not just to buy the fastest chip on paper. The right accelerator depends on what limits your application. If compute is the bottleneck, you care most about flops/S. If memory is the bottleneck, bandwidth and capacity become more important. A simple way to evaluate a chip is to ask three questions. Can it run the workload? How fast does it run? And what will it cost? Those three checks keep the decision practical. First, let's list the questions one by one so the decision process is easy to follow. The first check is compatibility. Before you worry about performance, make sure the hardware can actually execute the model or application you need. Once compatibility is established, we can move to performance and then cost. Next, measure latency or throughput, depending on your use case. This tells you whether the accelerator is merely usable or actually fast enough to matter. The final question is always about economics, because technical fit alone is not enough. Cost includes more than the purchase price. You also have to think about cloud pricing, or if you own the hardware, the upfront cost plus power usage over time. These three specs help answer the first two questions. flop/s for compute, and memory size plus bandwidth for data-heavy workloads. Once you know those, cost is usually easier to compare, especially because cloud pricing is often usage-based and fairly similar across providers. In this section, we'll look at how inference gets faster and cheaper without changing what the model is supposed to do. The key idea is that optimization can happen at several levels, and each level affects the system differently. A useful way to think about this is with archery. Better arrows are like model-level optimization. A stronger archer is like hardware-level optimization, and improving the full shooting setup is like service-level optimization. That analogy helps separate changes to the model, the machine, and the overall delivery system. In an ideal world, optimization would make inference faster and cheaper while keeping the model's answers the same. In practice, some techniques trade off quality, so you have to check benchmarks and watch for degradation when a provider changes the serving setup. This chart shows that the same model can perform a little differently depending on who serves it. The important thing to notice is not just the model name, but the inference system behind it, because that system can change real-world behavior. This figure reinforces the same point with a concrete experiment. Serving choices can slightly alter model quality. So when you compare providers, you're comparing more than raw model weights. You are comparing the full inference stack. We'll leave hardware design aside and focus on model-level and service-level techniques. Even so, remember that production systems usually combine multiple optimization methods at once, rather than relying on only one. In this section, we look at ways to make models faster and lighter without losing too much quality. We'll start with model compression, then move to speeding up decoding and improving attention. Model-level optimization changes the model itself to reduce compute or memory use, and that can affect behavior. For transformer-based language models, the biggest inference costs come from model size, autoregressive decoding, and attention. Let's begin with the most direct approach: shrink the model. The basic idea is simple. Fewer parameters usually means less memory and often faster inference too. Quantization and distillation are the two compression methods already covered in earlier chapters. Quantization reduces numeric precision, while distillation trains a smaller model to imitate a larger one. Pruning builds on the same intuition as distillation. Maybe not every parameter is equally important. The question is whether part of a large model can preserve most of its behavior. Pruning can mean two different things. You can remove whole nodes and change the architecture, or you can set less useful weights to 0 so the model becomes sparse without changing its total parameter count. After pruning, you can fine-tune the model to recover accuracy, or even use the prune structure as a smaller architecture to train from scratch. In practice, pruning can also help reveal better model designs. Some pruning results are impressive, with large reductions in non-zero weights and little accuracy loss. But it is less popular in production because it is harder to apply and many hardware systems do not fully benefit from sparsity. Among compression methods, weight-only quantization is the easiest to adopt and often gives strong gains right away. Distillation remains useful too, especially when you need a smaller model that behaves similarly to a much larger one. Now we move from shrinking the model to speeding up generation. Autoregressive decoding is expensive because tokens are produced one at a time, so even small improvements can matter a lot. If each token takes 100 milliseconds, a 100-token response takes about 10 seconds. That is why output tokens are costly. Generation is sequential, and every extra token adds latency. This is an active area, so the techniques here are snapshots of a moving target. The goal is to show the shape of the solutions, not to claim the field is settled. The first strategy is speculative decoding. It uses a small fast model to guess several tokens ahead, and then lets the main model check those guesses. Think of it as a proposal and check process. The draft model suggests tokens quickly, and the target model decides which ones to keep. Let's set up the notation first. We start with the tokens already known to the model, and then ask how to generate the next part efficiently. First, the draft model produces a block of future tokens in one shot. This is what creates the speed-up opportunity. Instead of predicting just one next token, the draft model proposes several. Those proposed tokens are the sequence that will be checked next. Next, the target model examines the draft tokens in parallel. That verification step is much cheaper than generating the same tokens one by one. The key advantage is that verification can be parallelized. So even though the main model is still doing the final judgment, it is doing less sequential work. After verification, we keep only what the target model approves. The system accepts the longest valid prefix of the draft sequence. That prefix rule matters. We move forward only with the tokens the target model agrees with from left to right. Anything after the first mismatch is discarded. Then the target model adds one more token of its own. That extra token keeps the process correct and advances the output. If the target model accepts J draft tokens, it then generates the next token itself. That keeps the sequence anchored to the stronger model. After that, the loop starts again using the extended context. Over time, this can reduce the number of expensive target model decoding steps. The benefit depends on acceptance. If none of the draft tokens are accepted, you get little advantage. If all are accepted, you get the maximum gain from each iteration. This diagram shows the flow clearly. The draft model proposes multiple tokens, and the main model only keeps the part it agrees with. Watch for the accepted prefix and the extra token added by the target model. This figure summarizes speculative decoding in one picture. The important idea is that the fast model proposes and the main model decides what survives. A bad draft model can create extra work, but the method is designed to avoid that trap. The next points explain why it still speeds things up in practice. The first reason is that verification is parallel, while generation is sequential. That difference alone can make checking much cheaper than producing tokens from scratch. This is the core performance argument. Speculative decoding shifts more work into a parallelizable form, so the model spends less time stepping through tokens one by one. The second reason is that not all tokens are equally hard. A weaker draft model can still get many of the easy tokens right. That uneven difficulty is useful. If the draft model matches the easy parts often enough, the acceptance rate stays high and the speedup becomes meaningful. The third reason is hardware efficiency. In decoding, the system is often waiting on memory, so some compute cycles can be used to verify draft tokens almost for free. Because decoding is often memory bandwidth bound, there can be spare compute available. Speculative decoding can use that idle capacity for verification instead of leaving it unused. How well this works depends on the task. Structured text like code often gives higher acceptance, and the draft model should ideally share the same tokenizer as the target model. Real systems have shown large wins, including major latency reductions for very large models. The point is that the draft model can be much smaller and still deliver a strong end-to-end speedup. This approach is popular because it is practical. It does not change the model's quality, and it is straightforward enough to appear in real inference frameworks. That makes it a strong production option. Next is a different idea. Instead of using another model, we reuse text from the input itself. This is especially useful when the output is likely to overlap with the prompt or source document. Here the model can avoid regenerating spans that already exist in the context. That can help in document question answering or code editing, where the answer often borrows directly from the input. This is similar in spirit to speculative decoding, but the draft tokens come from the context instead of a separate model. The hard part is finding the right span to reuse at each step. The advantage is that you do not need a second model. The trade-off is that it only helps when output and input overlap a lot, such as in retrieval, coding, or conversation. The figure shows where copied spans are reused in practice. Look for the highlighted regions, because those are the tokens the system can skip generating from scratch. This image shows two examples of reference-based inference. Notice how the reused spans are highlighted, which makes the copying behavior easy to see. These examples show the same pattern in two settings. The model reuses text that already appears in the input. The highlighted spans make the acceleration strategy visible. Now let's look at a more ambitious idea. Generate several future tokens at once. Instead of speeding up the usual chain, these methods try to break the chain entirely. Parallel decoding tries to predict multiple next tokens at the same time. That means the model is no longer waiting for each token before starting the next one. This can work because the existing context often already constrains the next few words. Even without knowing one token exactly, the model may still be able to predict what comes after it. Some methods use the same decoder repeatedly, while others add extra prediction heads. Medusa is a good example. It freezes the base model and trains small heads to predict future positions. Because these tokens are not produced one after another, they must be checked for consistency. Verification and integration are the crucial steps that make parallel decoding usable. The verification process starts by generating several future tokens in parallel. That gives the model multiple candidate continuations to test. This is the main parallel step. The model predicts k future tokens at once rather than marching forward one token at a time. Next, those candidates are checked against the context. The system is looking for coherence, not just raw prediction. This check matters because parallel guesses can conflict with one another. Verification makes sure the proposed tokens still fit the sequence. If some candidates fail, the model only repairs the bad ones. It does not need to discard everything and start over. That selective correction is what keeps the method efficient. Instead of throwing away all K tokens, the model adjusts just the parts that do not fit. The loop continues until the generated tokens pass verification and become part of the final output. This family of methods is often called Jacobi decoding. Medusa handles verification differently by building a tree of candidate continuations. From that tree, the system selects the most promising sequence. This diagram illustrates the tree-like selection process in Medusa. Notice how each head contributes multiple options, and the system chooses the best path through them. The figure shows how Medusa combines multiple predictions into one selected continuation. The key idea is to explore several options cheaply, then keep the best one. Parallel decoding is appealing because it breaks sequential dependence, but it is not as intuitive as speculative decoding. Some versions, including Medusa, are also harder to implement. Finally, we turn to attention itself. Even when the model is fixed, attention can be optimized by reusing work, shrinking cache costs, or using faster kernels. To generate a new token, the model needs the key and value vectors from earlier tokens. That is why attention becomes more expensive as the sequence grows. We can break the requirement down into a few steps. First, generating the current token depends on all previous keys and values. For token x_t, the model must attend to everything before it. That means the history up to x_1 has to be available. Next, when you move one token forward, the dependency expands by one more token. The cache keeps that from becoming a full recomputation. For x_t+1, the model needs the previous history plus x_t itself. Without caching, you would repeat the same attention work again and again. That is exactly what the KV cache does. It stores key and value vectors from earlier steps, so the model only computes the newest ones. This turns repeated work into reuse. This figure shows the cache in action. The important thing to notice is that past key and value vectors are kept, and only the newest vectors are added each step. This diagram summarizes the caching idea visually. Instead of recomputing attention history every time, the model stores it and reuses it. There is one important distinction to keep in mind. KV caching is an inference time trick, not a training time requirement. During training, all tokens are already known, so the model can process the whole sequence at once. That removes the need to cache past keys and values step by step. The key limitation is that attention work grows rapidly with sequence length, while cache size grows linearly. So the compute problem and the memory problem both become serious as context gets longer. With large models and large batches, the cache can become enormous, larger than the model weights themselves. That is a major reason long context inference is so memory hungry. Once the cache no longer fits comfortably in hardware, latency and storage become practical limits. Loading and moving that data can slow the whole system down. So attention is one of the main reasons long context is difficult. It is not just a modeling issue. It is a compute and memory issue at the same time. There are three broad directions for improving attention. Redesign the mechanism, make the KV cache more efficient, and write better kernels. Those three buckets cover most of the practical work in this area. In this section, we'll estimate how much memory the KV cache uses, and then look at the main ways people reduce that cost. The key idea is that cache size can quickly become a limiting factor during inference. Let's start with the baseline formula. This gives us the raw memory cost before any architecture changes or cache optimizations are applied. This line is just a visual separator, and it signals that the formula comes next. This expression multiplies batch size, sequence length, number of layers, model dimension, and memory per value. The leading two account for storing both keys and values. Another separator keeps the formula and the variable definitions easy to scan on screen. Batch size is how many sequences you process at once. Larger batches improve throughput, but they also increase cache memory. This separator leads into the next variable definition. Sequence length is the number of tokens in the context. This is often the biggest driver of KV cache growth. Next, we move from tokens to the model depth. Each transformer layer keeps its own key and value state, so deeper models need more cache. This separator introduces the width of the model representation. The model dimension controls the width of each layer's hidden representation. Wider layers mean larger key and value vectors. Now we finish with the storage cost per number. This is the storage cost of each number, such as FP16 or FP32. Lower precision reduces memory directly. Now you can see why this becomes expensive so quickly. With a large batch, a long context, and many layers, the cache can reach tens of gigabytes even for one model. Next, we move from estimating memory to reducing it at the model design level. These methods change attention itself, so they usually need training or fine-tuning. The important trade-off here is that you gain inference efficiency, but you're no longer using the original architecture unchanged. That means these ideas are not simple drop-in fixes for a train model. Local windowed attention looks only at nearby tokens instead of the full history. That shrinks the effective context window, which cuts both cache size and attention cost. A common pattern is to mix local and global attention. Local attention handles nearby detail, while global attention preserves the document-level signals that matter for the task. These techniques reduce the number of key-value pairs stored. Cross-layer attention shares cache across layers, and multi-query attention shares key-value vectors across heads. Group query attention is a middle ground. Instead of sharing one cache across all heads, it shares within smaller groups, so you can balance quality and memory savings more flexibly. In practice, these design choices can make a huge difference. For long chat histories, shrinking the KV cache can remove memory as the bottleneck and let you serve much larger batches. Now we switch from changing attention itself to managing the cache more efficiently. These methods focus on how the KV data is stored, compressed, or reused during inference. This is a practical bottleneck. Better cache management directly improves throughput and allows larger batches, especially when prompts and conversation history are long. Paged attention is a good example of a systems-level fix. By breaking the cache into blocks, it reduces fragmentation and makes serving more efficient. There are several other active approaches too, including quantization, compression, and selective caching. All of them aim to keep less data in memory without losing too much model quality. The third major strategy is to speed up the computation itself. Here we are not changing the model or the cache, but rewriting the low-level code that performs attention. A kernel is hardware-aware code for a specific chip. The best kernels use the details of the target device to move data and compute attention more efficiently. Flash attention is a widely used example because it fuses several transformer operations into one efficient path. The result is less memory traffic and faster execution. This figure shows the idea visually. Instead of many separate operations, the work is combined into a tighter, more efficient kernel. That fusion is what improves performance. This caption reminds us that the figure is illustrating operator fusion inside the attention pipeline. The main takeaway is that fewer separate steps often means better speed. Now let's zoom out from one kernel to the broader tooling around kernels. Compilers and specialized code generation help connect model code to the hardware that runs it. Kernels are small, specialized routines tuned for GPUs, TPUs, and other accelerators. They are built for repeated, performance-critical work. Matrix multiplication, attention, and convolution all have dedicated kernels. That specialization is one reason modern AI frameworks can run efficiently on different devices. To write a good kernel, you need to understand memory hierarchy and data movement. Performance depends not just on computation, but on how quickly data reaches the compute units. These kernels are often written in lower-level tools like CUDA, Triton, or ROCm. They give you fine control, but they are much closer to the hardware than Python is. Historically, only a small number of engineers worked on kernels because the barrier was so high. Today, both chip vendors and framework teams still rely on that expertise. As more engineers work on inference performance, these ideas are becoming more accessible. The next four techniques are the ones you'll see most often in practice. Vectorization means processing multiple contiguous values at once instead of one by one. That reduces overhead and makes better use of the hardware. This works best when data is laid out contiguously in memory, because the hardware can fetch and compute on larger chunks more efficiently. Parallelization splits the work into independent pieces that can run at the same time. That is how you use multiple cores or threads effectively. The key requirement is independence. Each chunk should be able to run without waiting on the others. When that is true, throughput improves a lot. Loop tiling reorganizes access patterns so they fit the cache and memory layout of the target device. It is very hardware dependent, so the best pattern changes across architectures. A tiling strategy that works well on a CPU may be poor on a GPU. The lesson is that locality matters, but the right access pattern depends on hardware. Operator fusion combines multiple steps into one pass, so intermediate data does not keep moving back and forth to memory. That saves time and bandwidth. If two operations touch the same array, it is often better to merge them into one loop. Fewer separate passes means less reading and writing of the same data. The first three techniques are fairly general, but operator fusion depends more on the exact model structure. That is why it often requires deeper optimization work. Because kernels are tuned for specific architectures, a new chip usually needs new kernel work. Flash attention is a good example of this hardware evolution across GPU generations. Finally, compilers lower model code into something the target device can execute. During that process, they often replace generic operations with specialized kernels whenever possible. Let's look at a real case study from PyTorch showing how much inference throughput can improve with different optimization techniques. The key idea is that these gains stack, but each step trades off effort, complexity, and sometimes accuracy. This figure summarizes how PyTorch improved Llama 7B throughput by applying a sequence of optimizations. We'll walk through each one so you can see how compiler support, lower precision, and decoding tricks each contribute to speed. First, the team starts with compiler optimization. This is the baseline step that sets up the rest of the performance improvements. Calling torch.compile lets PyTorch generate more efficient kernels for the model. The important point is that the framework can often fuse operations and reduce overhead without changing the model itself. Next comes precision reduction. Once the model is compiled, quantization can cut memory use and speed up execution even further. Quantizing weights to int8 replaces higher precision numbers with smaller ones. That usually improves throughput and memory traffic, while keeping the model close enough for many inference workloads. The next step pushes precision lower still. At this stage, the gains can be larger, but the risk to model quality also becomes more important. Moving from int8 to int4 makes the weights even smaller. That can deliver another jump in speed and memory efficiency, but it is also more likely to affect output quality. Finally, PyTorch adds a decoding strategy that improves generation speed without changing the core model architecture. Speculative decoding speeds up generation by proposing multiple tokens ahead and validating them efficiently. This is a useful reminder that inference optimization is not only about kernels and quantization. Algorithmic tricks matter too. This chart is the payoff. Each optimization step increases throughput, and the combined effect is substantial. Notice how the improvements build as you move from compilation to lower precision and then to decoding level optimization. This caption ties the chart back to the PyTorch experiment. The important part is not just the final number, but the sequence of techniques used to get there. The experiment was run on an A100 with 80 gigabytes of memory, so the results reflect a high-end GPU setting. One caution is that the source does not clearly report how these optimizations affected output quality, which matters when judging the trade-off. More broadly, compilers can be separate tools or built directly into inference frameworks. The main idea is the same in every case. Generate faster kernels for a particular workload, sometimes using vendor-specific or proprietary optimizations. In this section, we move from model design to service design. The focus is on using fixed compute and memory efficiently, so you can reduce latency and cost without changing model quality. Service-level optimization is mostly about scheduling and allocating resources across incoming requests. The model itself stays unchanged, so the goal is better efficiency without affecting output quality. A major theme here is batching. By grouping requests intelligently, An inference service can improve throughput and lower cost while still keeping latency under control. Instead of handling every request one by one, the server can process nearby requests together. That usually makes better use of hardware, but you have to balance the gain against the extra waiting time for individual users. There are three batching patterns to know: static batching, dynamic batching, and continuous batching. They mainly differ in how they balance efficiency against user-facing delay. Static batching uses a fixed batch size and waits until the batch is full before running it. That is simple, but the first requests in the batch can sit idle for a long time. Dynamic batching adds a time limit. The server runs the batch when it is full or when the window expires. That keeps latency bounded, but some batches may run underfilled, which can waste compute. The figure contrasts the batching behavior visually. Notice how the timing rule changes when the batch is launched and how that affects the trade-off between waiting time and compute efficiency. This figure summarizes the trade-off. Dynamic batching keeps latency manageable, even if it sometimes sacrifices a bit of compute efficiency. That is often a good deal in production systems. With naive batching, the whole batch finishes before any response is returned. For LLMs, that creates a problem when one request is much longer than the others because short requests have to wait for the slowest one. Continuous batching fixes that by letting completed requests leave the batch immediately. As soon as one slot opens up, the server can insert a new request, which keeps the hardware busy without blocking finished users. Look for the key idea in the diagram. The batch is not frozen. Finished responses can leave right away, and new work can take their place, which is why this strategy is so effective for LLM serving. This is the visual version of continuous batching. The important point is that it improves occupancy without making users wait for unrelated long-running requests. Next, we move to another service-level optimization for LLMs. Here, the idea is to separate the expensive prompt processing phase from the token generation phase, so they do not compete for the same resources. Prefill is mostly compute-bound, while decode is often memory bandwidth-bound. If you run both together on the same machine, they can interfere with each other and hurt both time to first token and time per output token. A common fix is to disaggregate the two phases onto different instances, sometimes even different GPUs. That way, the system can scale better and meet latency targets with less interference between jobs. The best ratio depends on your workload. Longer prompts usually need more prefill capacity, while shorter prompts or decode-heavy workloads may need more decode capacity to keep token generation responsive. Another useful optimization is prompt caching. Instead of reprocessing repeated prompt segments every time, the server stores them once and reuses the result across requests. This is especially helpful when many requests share the same system prompt or other repeated text. The first request pays the cost, and later requests can skip that duplicated work. Prompt caching becomes very valuable when the shared context is large, such as a long document or multi-turn conversation. In those cases, the saved tokens add up quickly. You may see this idea named in different ways, but the mechanism is the same. The cache stores reusable prompt prefixes so future requests can start from them instead of recomputing them. The image shows the repeated prompt segment being cached and reused. That reuse is what lowers both latency and cost when many requests share the same prefix. This figure makes the idea concrete. Once the shared prefix is cached, later prompts can skip redundant work. That is why prompt caching is so effective for repetitive workloads. For long system prompts, the savings can be dramatic. But the cache itself consumes memory, and building it into your own system may require real engineering effort unless the API already supports it. Many model providers now expose prompt caching directly. The exact savings vary, but the general pattern is consistent. Lower repeated input cost, lower latency, and some extra storage costs for the cache itself. This table shows that the benefit depends on the workload. The larger the shared context, the bigger the savings in both time to first token and total cost. Now we switch from request scheduling to compute parallelism. The goal here is to spread work across devices so larger or heavier workloads can be served efficiently. Accelerators are built for parallel work, so parallelism is central to serving at scale. The main families here are replica parallelism, model parallelism, and a few LLM-specific strategies like context and sequence parallelism. Replica parallelism is the simplest approach. Make multiple copies of the model and spread requests across them. The trade-off is easy to see. More replicas improve capacity, but they also consume more hardware. In practice, you have to match model sizes to available GPU memory. That turns serving into a packing problem. Which models fit where, and how many replicas of each should you place? This is the start of the placement example. The key idea is that once chip memory is fixed, serving becomes an allocation problem rather than a simple sizing problem. If hardware is fixed, you choose how to allocate it across replicas to maximize throughput and meet latency goals. For example, you might decide whether one large model is better than several smaller replicas on the same GPU. The second case flips the optimization around. Now the question is which hardware to buy or use, given a fixed replica plan. If the number of replicas is fixed, then the optimization flips around. Now you're choosing hardware to support those replicas as cheaply as possible. That case is less common, but it shows how the planning problem changes with the constraint. When a model is too large for one machine, you split the model itself across multiple devices. That makes serving possible, but it also makes scheduling and communication more complex. The most common inference approach is tensor parallelism. Instead of assigning an entire layer to one device, you partition the tensors inside an operator so several devices can compute pieces of the same operation in parallel. This technique helps serve models that otherwise would not fit, and it can also reduce latency. But the devices must exchange partial results, so communication overhead can reduce the speedup. The diagram shows how a matrix can be partitioned across devices. The key thing to notice is that each device handles a slice of the work, and those slices combine into the full result. This is the visual for tensor parallelism. It is a good example of splitting one operator into smaller pieces so the computation can happen in parallel. Pipeline parallelism divides the model into distinct stages and puts each stage on a different device. As data moves through the stages, different devices can work on different microbatches at the same time. Here the model is broken into a pipeline. Notice how work flows from one stage to the next, so devices can be busy at the same time instead of waiting for a single machine to finish everything. The point of the figure is the overlap. Once the pipeline is filled, multiple microbatches can be in flight across different stages at once. A large batch is broken into smaller microbatches, so each stage can keep working. After one microbatch finishes a stage, it moves forward while the next microbatch enters that stage. Pipeline parallelism helps fit large models across machines, but usually adds latency because of stage-to-stage communication. That is why it is less attractive for strict low-latency serving, even though it is useful in training. There are also more specialized strategies for long inputs. These are less common, but they're useful to know because they target the cost of processing very long context windows. In context parallelism, different parts of the input sequence are processed on different devices. That helps when the sequence itself is large enough that it benefits from being divided up. Sequence parallelism goes one step further and splits the needed operations themselves across devices. 4 long sequences that can make attention and feed-forward computation more manageable at scale. Let's bring the chapter together. We've looked at what makes inference costly, what metrics capture efficiency, and which optimization techniques matter most in practice. A model is only practical if inference is affordable and responsive. Lower cost makes AI easier to deploy at scale, and lower latency makes it usable in more real-time applications. We started with the basic metrics: latency, throughput, and utilization. For language models, latency splits into time to first token and time per output token, and the key takeaway is that faster response time usually competes with lower cost. Efficiency also depends on the accelerator underneath the model. That's why understanding the hardware is essential before trying to optimize a deployment. The chapter covered many optimization methods, but most application developers will rely on model APIs that already include them. Even so, knowing what is possible helps you judge whether an API is truly efficient. A useful distinction is whether you optimize the model itself or the serving system around it. Model-level changes can affect behavior, while service-level changes usually leave the model unchanged and only improve how it is served. At the model level, some techniques are general, like quantization and distillation. Others target specific bottlenecks, especially attention in transformers and autoregressive decoding in language models. At the service level, batching and parallelism are major tools. For autoregressive models, pre-filling decoding separation and prompt caching can make a big difference. The right optimization depends on the workload and the goal. Long contexts favor KV caching. Overlapping prompts favor prompt caching, and if latency matters more than cost, replica parallelism can help by spreading requests across more machines. Across many use cases, a few techniques stand out: quantization, tensor parallelism, replica parallelism, and attention optimization. These are the ones most likely to produce broad, practical gains. That closes the book's coverage of model adaptation techniques. Next, the focus shifts from individual techniques to building them into a complete system. As a reminder, inference means running the forward pass only. Training is different because it includes both forward and backward passes, which is why it is much more expensive. For a model provider, inference pricing has to cover the original training investment. The more the model is used, the more room there is to lower inference cost, although that logic is different for third-party providers serving open-source models. Different communities use the term memory-bound differently, so it is worth being precise. In this context, the distinction is between bandwidth limits and memory capacity limits. The roofline paper uses memory-bound to mean memory bandwidth bound. That definition is useful to keep in mind when comparing performance discussions across sources. Prefilling is the phase that sets up the initial key value cache for the transformer. That cache state is what makes later decoding steps possible. If a service is overloaded, separating urgent requests from batch requests can protect latency where it matters most. The batch path absorbs less urgent work, so the online path stays responsive. Prompt caching works well because parts of a conversation are often known ahead of time, especially the system prompt. The hard part is usually the unpredictable user query. There was a time when very fast chatbot responses seemed less human, so some systems intentionally added delay. That concern has faded as users have become more accustomed to AI assistance. You may also see different names for token timing metrics. LinkedIn uses time between tokens, and NVIDIA uses inter-token latency, but the idea is the same. This result is a useful rule of thumb for latency planning. It shows how expensive the input side can be, even though users often focus only on output generation. Flop/S utilization has long mattered, but MFU became a standard term more recently. It is a way to talk about how much of the chip's theoretical compute is actually being used. Peak numbers can sometimes be improved by testing favorable conditions that are not representative of real workloads. That can make a chip look better on paper than it is for actual users. Early neural networks were limited as much by hardware as by theory. Once compute improved, ideas like hidden layers became far more practical and the field moved forward. The GPU name reflects its history, but modern GPUs are general-purpose accelerators. The point is that the label is narrower than the hardware's actual role. Matrix multiplication is the workhorse of neural networks. Because it accounts for such a large share of operations, speeding it up has an outsized impact. Hardware and model design influence each other. A model can be built to fit a chip well, and a chip can be tuned to support a model architecture efficiently. Different GPU classes use different memory technologies. GDR is common in lower-end and mid-range GPUs, where cost and capacity trade-offs differ from high-end accelerators. At massive scale, the hard problem is not just compute but power, location, and network access. Cheaper electricity can come with higher latency, which is a real issue for inference services. During token generation, the model has to keep moving parameters from memory to compute units, so the process is often limited by bandwidth. Since only one token is produced at a time, compute utilization can stay low. That is why speculative decoding is less attractive when MFU is already maxed out. If compute is the bottleneck, you need a different kind of improvement. The Jacobi method is a good example of an iterative algorithm with parallel structure. Multiple parts of the solution can be updated independently, which makes it attractive for acceleration. Attention becomes expensive as sequence length grows, because the number of attention computations grows quadratically. That is one reason long context inference is so challenging. Not every model is transformer-based. Image generation systems like Stable Diffusion still rely heavily on convolution operations, so their optimization priorities can look different. Custom kernels can be a major competitive advantage because they reduce both latency and cost. For many companies, that implementation detail is valuable intellectual property. The balance between pre-filling and decoding is an important system-level metric. It helps explain where time is going in real workloads and where optimization efforts should focus. In practice, prompt caching often works best when earlier conversation turns can be reused. That means the service can skip recomputing repeated context and only process what is new. The same basic idea appears in training under a different name, data parallelism. The setting changes, but the goal is still to spread work across multiple workers efficiently.